Okay, what we're going to do here is we're going to take a look at series and parallel loads, just to remember your math. So what we're going to do is we're going to start out with series, and we're going to put two resistors in series. So if we were to draw our diagram, we would have a voltage source here, and let's go ahead and put, I guess, 120 volts, okay? And we would go to the first resistor, and then we would go through the second resistor, and then we would have our diagram there, okay? If we wanted to flatten this out into ladder logic, remember we would put line 1 here, and line 2 here, and loads go over here on the right, so we would kind of come here and put the first load and put the second load in series, okay? So what we want to do is we want to get a couple loads here, and we want to get some measurements, okay? So I'm going to take my first load right here, and I'm going to measure it with my multimeter. So I set my multimeter there. I want to get resistance, so what I'll do is I'll set this to resistance, because whenever I'm measuring a load, I want to get resistance. I don't want to do the continuity. That's for testing contacts. So I'll get my meter set up. I can kind of see it right there, and I'll go down this first one right here, and I'll go this one right here, and it says that I'm looking at about 9.9 ohms. Okay, that looks pretty good. So let's go ahead and get this one out of here. Why don't we just, for the heck of it, round that up to 10 ohms. So I would have 10 ohms right there. 10 ohms here, no matter, depending on which way you're looking at it. Now I'm going to go ahead and I'm going to get my next load. This one says 100 ohms on it. Let's just check it. Bring my meter in here. It's already set to ohms. And I'll go ahead and plug in here. And I will plug in here. And I have, okay, that one's 103.6 ohms. Just to simplify the math, why don't we round it up to 104 ohms, just for the purposes of this lecture. So I would have 104 ohms and 104 ohms. And so once again, this is for loads that are in series. Now, we're not going to see many loads here in series. Usually we're going to put loads in parallel, but we just want to review our math here. So if we go back to this diagram, we know that when loads are in series, we know that current stays the same, okay? And we know that resistance adds, okay? So if I take this circuit and I simplify it, I would have 120 volts, and then I would turn this into an R total circuit of 104 ohms plus 10 ohms. I got 114 ohms right there, okay? So I know that I can get the current here because I is equal to voltage over resistance, which would be equal to 120 volts over 114 ohms. Turn my calculator on here if I can get it to work. I don't want degrees. Let's see if it works. 120 divided by 114 gives me 1.05 amps. Okay, so now what I'd like to do is I've got two resistors here. So I'm going to go R, V, I, P. Those are my electrical quantities. Make a little chart right here. And my first resistor was for 10 ohms. My other one was 104 ohms. My current stays the same here. So if this produces 1.05 amps, as we calculated, 1.05 amps flows through each conductor, through each load, all the way back to the source. So I know that 1.05 amps is what I'm looking at there. So now I need to get my voltage drop for each one of these. Now these are different, so you know that you're going to be dropping a little bit differently voltage, right? So if I look at my formula and rearrange it here, I can see that voltage equals I times R. Okay? Which means that if I take the current times the resistance, in this case it's times 10, I'm going to get 10.5 volts. And then I take 1.05 times 104. Let's do that. 104 times 1.05. I get 109.2. Okay? So what we should be seeing is that adding these two together should get us pretty close to 120 volts, because in this case, this first resistor is going to drop a little bit of voltage, right? And then the second resistor, which is more resistance, is going to drop even more resistance, okay? And so when you add those together, you should be getting about 120, right? And so what is my V times I here? Yeah, 10.5. I'm a little bit off there. Oh, moving on. I need my power. My power is V times I. So I go multiply these together. 10.5 times 1.05 equals 11.03 watts. And just to check this for a minute, I don't know why that's still off, times 104. 109, okay. And when I multiply this V times I get this one at 114.66 watts. And that's how much each one of these is dissipating, how much heat. So this one is bigger, it drops more voltage, and it would dissipate more heat, 114 watts. This one is 11 watts, okay? And then if I wanted to check this, I could hook it up. And so to hook these up, be like this. They're in series. So according to my diagram, it basically left my voltage source. I remember using my meter as my voltage source, and it went into the first resistor. And then it came out of that resistor and went to the second resistor, and then came out of that resistor and completed my circuit. And that goes back to the meter right there. And I read 113.6. And that's close to, you know, what I would see here. Remember, we rounded up. We had 10 and 103.6, I think. We rounded these up. So adding these together, we do get about 114 ohms. So it looks like that is working, that the resistance in series adds, and we added them to get 114, and we measured it at 100 and right around 114, so that's good. Okay, so that was the series. Now, what we're going to do is we're going to take a look at these if we put them in parallel. Okay, so in a parallel, our diagram looks a little bit different. We would still have our 120 volts, and we would be going to a load, and we said this one was about 10 ohms, and then we went to another one here, which we said was about 104 ohms. If I wanted to make this into a ladder, I'd have L1, L2, and then I would run this over to the first load, which was 10 ohms, and then just as the flow right here at the 10 ohms has a choice of either going through the 104 ohm or the 10 ohm, the flow here, it has a choice of going through the 110 or through the 10 or through the 104 ohms. Okay, and so that's what that circuit would look like on the ladder. Now remember, on this one, what we have is voltage stays the same. On the series, it was the current stays the same. On the parallel, the voltage stays the same. Also, the resistance, 1 over R total, is going to be equal to 1 over R1 plus 1 over R2. So we're going to get our resistance. We're going to get 1 over R total equals 1 over 10 ohms plus 1 over 104 ohms. Let's go ahead and punch that up on a calculator. It's pretty easy in a calculator. 1 divided by 10, it equals, plus 1 divided by 104 equals, but now I need to flip this because this is 1 over. So I hit the 1 over x, I get 9.12 ohms for my total resistance. So here we go. We can look at this circuit right here and do our RVIP. And my two resistors remain the same at 10 ohms and 104 ohms. My voltage drop across this, because this is parallel, it stays the same. So each one of these would get 120 volts. Before we had calculated the current, and then we used the current to solve the rest. Here, we're using the voltage in the resistance, because that stays the same, to solve for the rest. So now what do I have? I have I is equal to V over R, which in this case would be 120 volts over 10 ohms divided by 10. I'm getting 12 amps. Oops, let's do that again. Yep, that's right. And then on the other one, I have 120 volts over 104 ohms. 120 divided by 104 equals 1.15. Okay? And once again, my power is V times I. So I take the first one here, 120 times 12 equals 1,440 watts. And then my second one, 120 times 1.15 equals 138 watts. Okay? So we're going to then go ahead and measure this and see if that seems to make sense. So I bring my resistors back in here, okay, and I bring my multimeter. What I would do is I would connect my multimeter up to the first resistor. And it looks like I'm reading, once again, 103.6. And then what we have to do is put them in parallel. So the top of this resistor just goes to the top of this resistor, and the bottom of this resistor just goes to the bottom of that resistor. And what happens? We read about 9 ohms on the meter. Okay? So I move these out of the way. I can see that my calculation, so that I should be reading right around 9.12 ohms. And it seems like we are reading actual versus our calculated is pretty close. Okay? There's one other thing that is interesting to look at. So what we had here was 120 volts. And this simplified into about a 9.12 ohm circuit. That was a simplification of this, and that's what we generated this from. So how much current does this generate? I equals V over R, 120 volts over 9.12 ohms equals 120 divided by 9.12 is about 13.15 amps. Okay, so in this case, we can see that in our RVIP, current leaves of the 13.5 amps leaves the circuit here, and apparently 12 amps of it goes through the smaller resistor, and then 1.15 amps goes through the larger resistor. Okay? So this is 13.15 right there, just showing you that was 13.15. And so these add up to 13.15. And how come that is? Well, it's because current takes the path of least resistance. So when the current flows out of here, it has a choice. Should I go through the 10 or should I go through the 104? This is the path of least resistance. So most of the current wants to go through this resistor, which is 12 amps, then this resistor, which is 1.15 amps. Okay? And so to reiterate, when we looked at the parallel, we kept the current the same. And when we looked, the series, we kept the current the same. In the parallel, we kept the voltage the same. Now it's interesting to note, and we're going to cover this quite a bit more in the class, when you add a resistor in series compared to when you add resistor in parallel, well, what happens? When you add a resistor in parallel, the resistance goes down compared to if you added it in series. This resistance, 9.12, is a heck of a lot less than 114 here. So just think about that. You're gonna need to study it quite a bit. When you put a resistor in parallel, the resistance goes down compared to series. So what does that mean for current? Well, if you have less resistance for the same amount of voltage, we had 120 here and 120 here, you're going to get a heck of a lot more amps. Here we got 13 amps flowing in the parallel circuit, and here we had 1.05 amps flowing in the series circuit, which is interesting if you think about it, because basically we just use the same two loads. And these same two loads, the 100 and the 10, depending on how you configure them, series or parallel, you're either going to get a lot of amp draw or a little bit of amp draw. Okay? So there's quite a bit in the reading material about series parallel circuits, the way that you install them in parallel and series, and how you run the calculations, and the mathematical relationships between them.